Okay, so what we're looking at here is one of the sensors that for use on the 300-ton machine that's used to detect when parts are down here on this discharge conveyor. The big issue we had with this machine a while back was that these sensors here and here were not set up the same. For some reason in the logic programming, it was set up that this sensor was light operate and this sensor is dark operate for whatever reason. So what that means is for each one to detect the presence of parts, the logic has to be looking for the sensor to be on in this condition, in this state over here, and then off over here. So the issue is if you have a problem with one of these sensors, you would normally think that you could just switch them out from one to the other. But you can't, because the logic is in the machine is written as such to accommodate one of these things being light operate and one of them being dark operate. So if you go to switch them in your troubleshooting process, thinking, oh, maybe the other one's fine, I'll switch it over, it's not going to work, and it's never going to work because the logic in the PLC is looking for a different state. So this example of the issue that we had here was the whole reason that we wanted to talk about light operate and dark operate and why it's so important, because it basically reverses the logic. It doesn't change the logic in the PLC, but it provides the PLC with the exact opposite information that it needs. So it's not detecting the condition properly. In a case like this, we weren't able to debug this normally. Actually had to hook up the PC, look in the logic and see that there was two different logic states for these two sensors, and that's how we found out. Ultimately, we reprogrammed it so that both are light operate. When they receive light back, the output goes high. So now these two sensors are interchangeable, and the logic is the same for both lanes. Okay, so this is the first sensor on the list. This is the Telemecanique sensor. You recognize this, the big giant case here, 120 volt sensor. I believe the sensor is ultrasonic. Ultrasonics are great for level detection, particularly when you're trying to detect the level of liquids or sticky things that you wouldn't want to do with a contact measurement sensor. The great thing about ultrasonics over light is the fact that ultrasonics are not affected by the transparency of the material you're trying to detect. So, in other words, the reflectivity or the amount of light that you're getting back isn't a factor here. You can imagine you'd have a lot of light coming back if you were doing a white pipe dope, but if for some reason we were doing a clear or semi-transparent, then you'd have a different reflectivity, a different amount of light coming back to that sensor, and you'd have different settings. Well, the use of an ultrasonic sensor can help you do that surface measurement, if you will, surface level control without contact and without the general effects that you have with reflectivity and the amount of light coming back. So it makes something that's a sensitive situation into something that's not sensitive at all. It's either on or off, and there's very little influence from what it's detecting on how it works. We'll talk a little bit more about that in a second. Okay guys, the next sensor on the list that I have on my list here is the Keyence LR-ZB series sensor. This sensor is being used at the AAV assembly station. Here it's being used for parts presence. So the sensor is detecting the presence of the diaphragm in this particular case to make sure the diaphragm is there, to provide the information to the PLC to either cycle or not based on the presence or absence of that part. Typically for parts detection from an engineering perspective, I like to do things with through beams when possible. If they're non-metallic and we can't use a prox, I'd personally rather use a through beam, because then you have a blocked or unblocked state rather than setting a threshold for how much light is coming back. In a situation like this, it's very difficult to package a through beam where you have an emitter and receiver on either side. So sometimes the machine execution dictates the type of sensor that you have to use. The disadvantages of this, though, is that you have to set a threshold, so it's not a dumb on or off. And that threshold is based on the amount of light coming back, which could possibly change from part to part, or especially if you're using different colors of parts, that reflectivity of how much light's coming back can vary. So when we use sensors like this, we always want to set the thresholds somewhere in the middle of being able to detect and not detect all the parts that it's going to see. So if you know you've got a part that's got particularly rough edges or something like that, or a matte finish that may not reflect as much light, you want to be able to detect that equally as well as a part that may be shiny and be able to send more light back. Okay, this one's going to be familiar to you guys. This is the Banner MAID 9 series reflective style sensor. This is the low level detection at the PSA dauber chute. And this is another application where through beams for me are always the best to work with. But again, sometimes packaging, sometimes influence from a vendor influences the decision on which sensor to use. But regardless, this is the application here. It is relatively straightforward because rather than a part reflecting light back to the sensor, you've got the reflector on the other side reflecting that back. So it's a little bit more robust. It acts more like a through beam with emitter and receiver, but just kind of keeps things a little bit easier. Again, sometimes you want to do this for machine accessibility. If we had an emitter and receiver in this application, if something was wrong with the receiver, we'd have to find our way around to the other side of the machine over there to fix it. So in this case, with the convergent photo eye here, if something's wrong with this, it's going to be here, something's wrong with the sensor, everything's right here in this accessible area, as opposed to being something wrong over there. It's just a reflector, right? So that's probably one of the reasons why the machine integrator decided to use a convergent reflective sensor in this application. So here we are at the dauber bowl. This is, to me, is a classic execution of a through beam used for part level control. We got the emitter and receiver pair here mounted into this tooling, into this bar, and of course the fibers are going back to the amplifier here. We're shut down right now, so don't see anything. But this is a case where you can build these fibers into tooling so they're protected. You've got accessibility on both sides, so it's not a big deal that you have an emitter and receiver pair here. It's not a big deal. Yeah, I don't think too much more to talk about here. Now, as with any sensor, the first thing to consider when troubleshooting these things is, am I getting a signal and am I not getting a signal because I'm not aimed correctly? One of the advantages of using through beams, particularly when you can build them into tooling like this, is that you inherently have your alignment between your emitter and receiver built into the tooling. The other thing too is to consider on the previous sensor, the alignment of that reflector. That has to obviously reflect back to the sensor properly. So alignment's always a big deal. And usually with through beams and applications like this, you can build them into tooling so you never lose the alignment. There's all different kinds of fiber configurations you can have down here that enable you to bury these things into tooling. So once you have an emitter receiver pair, you kind of just forget about it unless you accidentally pinch one or something, and alignment's never an issue. Now here you may not have issues with alignment from emitter to receiver because it's on this same piece of tooling, but you may have issues with alignment based on the position of this tooling. Swinging around, and then also, of course, up and down. Now the one thing you'll notice that both of these level control sensors, whether it be this through beam or that other reflective one, is that they're mounted at an angle. And that's so you don't get misreadings. If you look at these daubers, if you were to shoot a sensor, a beam, whether it be a through or reflective, straight through here, there's a possibility that you could get blow-by of that light in between there and get a false reading. By going at an angle, you see that no matter what, at some point, no matter which angle you come through here, you're always going to be blocked by the overlap of a dauber. The daubers start, right, when you start looking at two daubers in a row, you start going in an angle, you start getting dauber overlap. So it's kind of like a fail-safe that as long as there's a dauber there, you're never going to have an opportunity for blow-by. As long as you're at the right height, which, you know, it's all part of that alignment. Okay, here's one of our examples of the use of the Banner Q4 series, Q4X series sensor. You guys have probably learned this thing has a lot of horsepower, a lot of different settings and whatnot. So we're using it here for dauber bowl level detection. The interesting thing about this thing, and I don't know if you guys went over it or not, but when you start going to laser sensors, laser-based sensors, you can start doing a lot of things because you actually get a measurement. And that's essentially what this sensor is doing. It's measuring the level of the parts in the bowl to start and stop the elevator. We went through a significant design of experiments over the summer to determine what best setting this needs to be at. And I think there's two different ones that Joe found out. Anyways, the big thing with this is when you're using lasers to measure stuff, you can obviously use that to turn things on and off based on whatever threshold distance you set. But the other cool thing about these things is you can have what's called foreground and background suppression. So that means if I wanted to look at something in between here, I can do that with a laser sensor and not worry about the reflective background down here. Because you can set this up to say, you know what, I'm interested in knowing a certain distance or the presence or absence of something in between here, and I don't care, like this lower section here where my finger is, I don't care about anything beyond that. So when nothing's here and the sensor's now reflecting off the bottom of the bowl, you can set the sensor up to say, hey, I don't want to ignore that. I don't care about that. And the same thing with anything before, in front of the sensor, between this band. So what I'm describing is a function of the sensor. We are not using that in this particular case, but you know, just recognize that these sensors are extremely powerful, and when you use a laser as a distance-based measurement of what's there and what's not, you can ignore things in the foreground and ignore things in the background. Pretty neat. Anyway, this is a pretty high-powered sensor that we're using just to detect level, but so be it. That's what it is. So before I leave here, saying level made me think of something. So we're talking about, you know, how ultrasonic sensors are great non-contact level detection sensors that are kind of impervious, if you will, to reflectivity and the reflectiveness of the material. The reason why we don't use ultrasonic sensors here, because ultrasonic sensors are essentially working off of vibrations, almost kind of like radar. This is a vibrating bowl, so ultrasonic sensors are going to be really, really confused if you use them here. Okay, here we are at the new putty machine. This is also another application for the Q4X series sensor. We're using it for level control here, mainly because, you know, all putty is kind of the same color, same consistency, so we're not going to get a lot of variation from reflectivity on this sensor. And then the big thing about this sensor is that it has the capability for two outputs. So, and what's driving that is we want two different things to happen at two different points. So this is doing level control inside the hopper, right? So we want one thing to happen when it's high. When it's high, we want that output to tell the machine to close that valve so that no more putty comes in. That's different than what we want to happen at the bottom. At the bottom, we want the machine to stop, because we found that as the machine processes, if the level in the hopper gets too low, then the machine starts getting light, or the cans start getting light, and we start getting rejects because of lightweight cans. So we've got the same sensor giving us two different pieces of information that we need to do two different things with. That's why the dual output or two output capability of this sensor is so important. Okay, last but not least, we're back at the 300-ton machine. These are little Hall effect reed switches. You guys have probably played around with these in class. It's mounted right in here, right into the cylinder. Those are using basically inductance of the metal piston inside. So as that piston in the cylinder moves up and down at its retract and extend positions, you can get an indication that that cylinder went full stroke. There's different ways to look at these. A lot of machine integrators like to work with these because they can route these sensors, the wires for the sensors, right along with the pneumatic tubing that actuates the cylinder. But some of us purists don't like them as much because we would much rather sense what's happening at the tooling end than necessarily what's happening at the cylinder. If you think about it, this cylinder could still be going up and down, and your machine is recognizing that the cylinder is going up and down. However, there's a excuse me. There's a possibility that the tooling up here may have broken off, and you may not necessarily know it right away. So I'm kind of a purist, and I would rather use a prox sensor to detect the position of the tooling, whether it's all the way up or all the way down like it's supposed to be. But again, a lot of things have compromises. There's a lot of good reasons to not do the purist or what you might think is the best thing. Again, it all comes down to machine packaging. Putting prox sensors in this area in the 300-ton machine where this plate's coming up and down isn't really going to work. It's going to interfere with the product flow. It just wasn't an executable thing to do in this particular case. Unlike at AAV, if you look at the end-point sensing on the cylinders in that machine, those are all with proxes on tooling. So that's a little bit more of my traditionalist approach. But it is kind of old school as far as that goes. The Hall effects are a little nicer to integrate, and again, you can share that cable routing with the cylinder air routing a little easier sometimes than you can with the larger 3-wire sensor cables that are coming off of proxes. But never a perfect solution. There's always a best solution, though, or an optimized solution. So that's some of the thinking that goes behind, why you'd use this type of sensor versus proxies and stuff like that.